Welcome to this video on Kepler's third law of planetary motion. This is the law that introduces time into the celestial mechanics of planets, and it can be extrapolated to many other things in the universe. So I'm going to use examples of, as we have in this past few videos, of the mass of a planet and the mass of the sun as the interacting system. However, you can use this law for binary stars, you can use it for moons or other artificial satellites, so it works in many different forms. So one important term here that we need to make sure we understand is this term period. And most of the time we use this uppercase T to represent the period of the circular motion. So the period is the amount of time that it takes the planet to make one complete revolution. So one complete revolution is 2 pi radians. And so if we put that kind of in this form, to make a complete cycle, it would take X number of seconds or hours or days or years and so on. So there's many different units that we can use, and we're going to analyze that in just a little bit. Now, Kepler's third law actually relates this periodic motion, or the period of motion, to what is known as the semi-major axis, which for all intents and purposes can be this average radius of distance between the sun and the planet in question. And so what we're going to do here is we're going to start by doing a little derivation that we did in the previous video, which was to set the gravitational force equal to the centripetal force. We then went and fleshed that out so we could see how all the variables related to one another. So it looked something like this. Okay. We then made a couple simplifications where we saw that the mass of the planet actually is removed. One of the radii cancels out, and we're left with v squared is equal to g times the mass of the sun over r. Now what we're going to do is we need to incorporate this variable period. One way to do that is if we're assuming roughly a circular orbit, we can say that the tangential speed is approximately 2 pi r over t. So this is just the circumference for one complete rotation divided by the time that it takes to make one complete rotation. Now I'm going to go ahead and substitute this in for v over here. And so what I'm going to end up with is 2 squared, or 4, times pi squared times r squared over period squared. And I'm going to set that, as it shows here, equal to gms over r. Now I may make this an uppercase r just to match the way that I wrote it here. Now what I'm going to do is I'm going to move some things around because I know what Kepler's third law is supposed to look like. And what it tries to tell us is the relationship between t and r. And so we want to get t and r on opposite sides of the equal sign so we can make some simplifications here. I'll start by multiplying t squared onto the other side and multiplying r onto the other side. So what I'll end up with is 4 pi squared times r cubed equals g times the mass of the sun times t squared. All right. Now I'm going to do one more thing here to get t squared by itself. I'll divide by g over ms. And that's going to leave me with the following equation, which relates t squared to the cube of the radius. So the final equation here would be t squared is equal to 4 pi squared over g ms times r cubed. Now what that law says in everyday language is that the time the planet takes to make a complete rotation is proportional to its semi-major axis, which is the distance away. Now what it's saying mathematically specifically though is that the square of the period is proportional to the cube of the radius. So if we were to graph the cube of the radius on the x-axis and the square of the period on the y-axis, we would get a linear line with a slope equal to 4 pi squared over g times ms. And what's interesting about this is that this slope is constant because the mass of the sun, we're saying in these situations, is constant. G is a universal constant, pi is a universal constant, and 4, of course, is constant as well. So what you could do is you could actually plot all the planets onto the same graph, and they would all actually fall on the same line, which is pretty cool because they all share these things in common between their rotations. So Kepler's law of planetary motion is sometimes stated most concisely as the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit, with the semi-major axis being roughly the average distance between the planet and the object it's orbiting, in this case the sun. One last thing I'd like to state about this is that if we use very specific units, this equation actually simplifies down even more. The units that we've devised to describe these situations are to use what are known as astronomical units, or AUs, which is the distance of the Earth to the Sun. And so if we measure everything in increments of that distance, that can help us make for much smaller numbers. We also then describe different stars in solar mass amounts, which we usually symbolize with this little image like this to show that it's the mass of our sun. So this would be, the mass of our sun would be 1 solar mass. We then also take T to be Earth years, because remember that if we take a year to be the amount of time that it takes a planet to go around the sun, say a Neptune year would be very different than an Earth year. But if we say these three things here, that the distance r is in astronomical units, the mass is in solar masses, the period is in Earth years, then what ends up happening is the constants 4 pi squared over g actually just condense to 1. And so this equation can be written then as t squared is equal to r cubed, which is pretty cool. In this case, you would obviously have to use all these same units if you were making comparisons between other planets. What's really neat about this law, though, is just with one little addition, you can actually use it to figure out the orbital period of binary stars or binary orbits. And the only thing you have to do there is we're going to expand the m term to be the mass of the two things that are orbiting each other instead of just the one thing being orbited. And so you'd have something that looks like this. So hopefully you find that interesting. Basically, it's saying that the further you are away from the sun, the longer it takes you to make a complete orbit. And so, for example, we haven't known Pluto for very long. Pluto was only discovered in the 20th century, in the early 20th century, and its orbital period takes a couple hundred years. And so, since we haven't been able to watch Pluto go around the sun one whole time yet, we can still make a prediction about how long it will take to go around the sun based on this law.